Okay, so this is a set of tips for ESA Level 3 Physics, Exercise 7C. I'm going to start with question 1. An open railway wagon, some rain falling in it as it travels along a track, and so an appreciable amount of rain builds up into the wagon, which seems kind of unlikely, but anyway, that is what we have. So by considering conservation of momentum, explain what will happen to the speed of the wagon. Well, what you need to do here is think about what's going on here as the raindrops fall into the wagon. So what force are they applying to the wagon? Which direction are they falling? What force does that produce? What resists that force? And then think about, does that add to the momentum of the wagon? And if not, what does it add to the wagon? And what's momentum made up of? Because if the momentum of the wagon is constant, for example, but the mass is building up, then this might have an effect on the velocity of the wagon. After all, P equals mv. And so that's your goal there, is think about what's happening with that rain. Secondly, part B, the rain stops and a drain plug is opened in the bottom of the rolling wagon, allowing the accumulated water to run out. So very similar to the first one, you need to think about the water that, in this case, is leaving the wagon. What's going on with the water that is leaving the wagon? Oh, my video's just decided to go back to part A and talk about the effect on momentum and therefore the speed of the wagon. That's unhelpful. Okay, so we'll get back to part B. So B, sorry about that. So part B, what's happening when the water falls out of the wagon? What momentum does that water have as it falls out, and therefore what is happening to the momentum of the wagon? What is happening to the mass of the wagon, and therefore what is happening to the speed of the wagon, if anything? And particularly think about the movement, how the water that is falling, how that is moving after it leaves the wagon. That's going to be your core way of thinking this through. I did a lot of writing when I wrote some notes about this question, and it's taking its time to keep up with this. Okay, question 2. This is a game of pool. This is a very fertile ground for collision type situations. In this case, we're talking conservation of momentum in 2 directions. A white ball is fired at a coloured ball, and we have to draw a vector diagram to show the total momentum of the 2 balls after the collision. And really all you need to remember is that momentum is conserved. Momentum is conserved. So if you can draw a vector that shows the momentum before the collision, that is the same momentum that the system has after the collision, and is asked for the total momentum. Okay, part B, write a vector equation to show how the total momentum is related to the individual momentum of the 2 balls after the collision. Well, I think it's very useful in this situation to draw a vector for each ball. So so showing the momentum of each ball. The white ball, for example, has a momentum up and to the left, and the coloured ball has a momentum down and to the left. And so you can draw those 2 vectors, and you can then do a vector addition, that the total momentum, which is the same as the momentum before, equals the momentum of the white ball plus the momentum of the red ball if you add them nose to tail. Part C, here's your point of drawing a vector diagram of which we've actually just done. So the first one was a vector equation. Now you're actually going to turn it into a vector diagram and use that, and Pythagoras' theorem, to show that the size of the momentum of the coloured ball is 0.11 kilogram meters per second. Part D, calculate the speed of the coloured ball. Well, if you have its magnitude of momentum, you can use P equals mv. Part E, calculate the angle through which the white ball was deflected. Again, you can use your triangle and SOHCAHTOA to solve for the angle of deflection of the white ball. You just have to choose which angle in your triangle is the relevant one. Okay, question 3. The game of curling, which has been on TV in the Winter Olympics. I'm sure it's been on TV, I haven't seen it, but lots of curling at the Winter Olympics. Draw a vector, so we've got a curling stone slid along toward the T, wax into another curling stone. Draw a vector diagram to calculate the size of the change of the momentum of stone A. So the key thing here is that stone A has been deflected has been caused to deflect through an angle of 90 degrees. So when you think about your situation, the stone A was traveling, and so the way I'm drawing it, to the right with a certain momentum, 47 kilogram meters per second. And after the collision, it is traveling directly down with a momentum of 8.6 kilogram meters per second. So you should have two arrows for your vector diagram to use. Firstly, am I going to figure out what I'm trying to solve here? Yes, I'm just watching my video to see whether, I think I was just drawing the whole situation first. Maybe I should have just focused on the question. Now, what you're going to do is draw a vector for the initial momentum and for the final momentum. But the change in momentum, which is what you've been asked for, delta P equals PF plus negative PI. So you're actually going to want to reverse the direction of the PI arrow. So you've got a negative PI, which is to the left, and you're going to want your PF is down, and you add the two together, and you get the nose to tail, and you get the change in momentum, which should be a long arrow pointing mostly to the left but somewhat down. B. Calculate so that should be a triangle, of course. B1, calculate the size of the momentum of stone B after the collision. Well, this is just the same as the size of the change in momentum from your diagram. Change in momentum of stone A equals negative of the change in momentum of stone B. Explain any assumptions you've made. Well, it's the standard assumption for conservation of momentum, which is that there is no external force acting, so that the momentum of the system is conserved. Part C, draw a labelled arrow on a vector diagram to show the direction of the momentum of stone B after the collision. Well, that's really just the opposite of the momentum, the change in momentum of stone A. I'm not sure about why you would do that on a vector diagram as opposed to draw it. Yeah, you could draw it on the same diagram, I guess. Part D, after the collision, stone A goes on to hit the T. After this collision, stone A and the T are traveling at right angles to each other. The T with a momentum of 4.2 kilogram meters per second. So really, it's just the same thing. You're going to draw a vector triangle that includes the, probably in this case, the momentum of stone A before and the momentum of the T and of stone A after. You've been told that they are going off at right angles. So the triangle is set up differently, but you need a triangle. You need the three momentums, the momentum of A before, the momentum of A after, and the T after. Those after momentums should add up to the before momentum, and you can solve the triangle. Question 4. At a bowling alley, a 6.8 kg bowling ball is traveling forwards with a momentum of 44. Hits stationary pin. Calculate the momentum of the bowling ball after the collision. Well, you're going to do that using P equals mv. You've been given the mass and speed of the pin. Draw a vector to show the size and direction of the total momentum of the bowling ball and pin after the collision. Conservation of momentum, P before equals P after, and you've been given the momentum before. So, well, you have been given the momentum before and its direction. Part C, show the size of the momentum of the pin after the collision is 24. So here the prop thing is that they come off at different angles. So like in previous questions, you need to use a vector diagram, not just a direct subtraction. Part D will be able to be calculated from that diagram. Part E, so you're going to use Sokotoa in Part D. Part E, you need to explain why the size of the change in momentum is the same as an answer to C. I would use Newton's third law, which is the action-reaction law. Part F, if the bowling ball and pin are in contact with each other, you need to use delta P equals F delta T. And you have been given, you've already calculated delta P earlier in this set. 5A, well, this is a two-dimensional top view of a rock exploding if you read through carefully. The side diagram is not, but what I would do is sketch the top view. And the first thing to keep in mind here is, what was the momentum of the system initially? Well, the rock was not moving, so the initial momentum of the system was 0. And after the collision, the momentum of the system has to still stay the same, which means it has to be 0. So if rock A is traveling north and rock B is traveling west, then rock C, the remainder, must be traveling sort of southeast. You're then going to go on and you need some more information. Now, you've been given the total mass of the rock. You've got mass of rock A, mass of rock B. So rock C is everything left over. This is a good explosion. It only creates 3 rocks and not lots of dust and stuff. So you can work out the mass for mass C from as the leftover. You can work out the momentum of rock A because you've been given its speed and its mass. You can work out the momentum of rock B because you've been given its speed and its mass. You have directions for A and B. You really only have one thing left to find after you've found the mass of rock C, and that is two things, the speed and direction of rock C. And that's what, not surprisingly, they've asked for. So the starting point is that if the total momentum is 0, then the vectors for the momentum of PA, PB, and PC added nose to tail like this should add up to 0, and rocks A and B are at right angles. So that is quite a soluble little triangle using Pythagoras' theorem for the magnitude of the momentum of rock C, and Sokotoa to solve for the direction of rock C. Thank you for listening.